All right. Hi, thank you for coming. Happy Tuesday. Um, Sorry, I ran out of time and I don't have like a plan, but I have the plan in my head. And the plan in my head is it's time for a new unit. I have graded the graph video. So if you've got questions on that, let me know. I have also sent out a reading that hopefully you did today to prepare you for our discussion, just to kind of remind you about here's how recursion works, because we're going to go into this new unit of dynamic programming. And dynamic programming is all about solving these fairly difficult problems. So there's a pretty good chance that you'll still be using the graph techniques, like knowing that terminology and being able to approach those kind of problems is still going to be useful. Dynamic programming as a whole is fairly difficult, and so we're going to probably spend the rest of our time in this class practicing. So there's a new unit up. The reading is here in case you wanted to refer to that again. I've got the slides here and the packet. Maybe I will reorder this so that it makes sense. So the slides and the packet, and there will be a video assignment. The video links, I'll pause the recording for a second and show you this. Okay, so I know what the problems are. Their longest common subsequence, if there's an equation that gets you paid and you have to figure out what's the best way to put parentheses so that you get the most amount of money, and other problems. So I will assign these and this will go out to you tomorrow morning at the latest. So I just need to finish editing the video assignment and that'll be ready. Currently, I have it due the Friday of the last week of class. But since you're already working on the project, I encourage you strongly, very much, please, to finish it earlier. So the video problems are set. I will just distribute them. Okay. And then the packet we will talk about as we go through. Okay. So we're starting a new unit, dynamic programming. Hopefully you had a chance to do the reading. So what we're gonna do is we're gonna briefly give some motivation of here's some hard problems without maybe you use information that you learned from the reading, but otherwise just very quickly think about how do we try and solve them, and then we'll go into actually what is dynamic programming and talk about the two types. We'll solve an example problem, or we'll see the solution for an example problem, which is the knapsack problem. I've given the group assignments and we'll talk about packets. So that's where we're going. So just to be open, so the textbook, this is where most of the problems are coming from. The textbook, I will say, so I struggled a little bit in prepping this unit because the algorithm design manual focuses a lot on recurrence relations, which we haven't really gone into. So that's why I pivoted to the cracking the coding interview chapter. And there's also a slide deck from someone at the University of Texas at Arlington that was really helpful. So if you go to that link, you'll see some similarities with this one as well. Okay, so I think we're gonna see some problems, and I want you to talk with your neighbors, just kind of brainstorming how do we try and solve this, or what are the sticking points in trying to solve these difficult problems. So the first one is a knapsack, and I might skip over this because we'll do it later. But a dynamic programming problem includes if we're given a knapsack with a fixed capacity, so like my backpack can only carry, I don't know, 15 pounds or something like that. And we have some objects that we want to transport that have some weight and a cost or a value, how do we decide which objects are going to fill that knapsack with as much weight as possible? So getting as close to the weight limit as we can, but not going over, and with minimal cost, or depending on how we phrase it, with maximal cost. So it kind of depends on the problem phrasing. So be very attentive as you're reading problems, because so this one says with minimal cost. The version we'll look at later, I believe, is with maximal cost. So just be careful, read carefully. Yeah, I think I will just say with maximal. The more mathy way of saying that is given a set of items, each with a weight and a value, determine which items to include in the collection so that the total weight is less than or equal to a given limit. So the given limit, that's the capacity of the bag, and the total value is as large as possible. So this is a case where we're looking for the most. So we'll look at this one later, but let's look at another one where let's imagine a robot sitting in the upper left-hand corner of the grid. So maybe we're up here. And this grid has R rows and C columns. And the robot can only move in two directions. So only right and down. Those are the two options. And so we want to get from the top left to the bottom right. And maybe there are some cells that are blocked off. And so we want to design an algorithm to find a path for the robot that goes from the top left to the bottom right. How do we determine what that path is? So talk with your neighbor for a moment. If some of these are blocked off, so if this is clear, then maybe that's the best path. What if there is a block here? Talk with your neighbor. Brainstorm for a second. Okay, let's come back. So thank you for taking this time. We're going to pause this because it's one of our packet problems. So this is just brainstorming practice. I've got another problem for you to think of, just to brainstorm, which is you're a very popular actor and you're offered N jobs. And these jobs have a start date and an end date and some salary. And you want to figure out which jobs are you going to take so that you make the most money. And maybe add on to that of the most jobs to take additionally so that you have maybe least downtime as well. You can discuss if you want the most downtime or the least downtime. Yeah. Yes. So yeah. So if one job goes from April 1st to April 30th, and another job is like April 15th to May 15th, then you can't take both of those jobs because they overlap. Okay, brainstorm, go for it. All right, let's come back. Thank you again. Make any notes if you need to, based on your conversation. Otherwise, so this one is problem 1 The robot grid is problem 2. So make notes if you need to. Otherwise, we're going to talk about what is dynamic programming. So it's a combination of two things, recursion and writing things down. That's it at its most basic formula. You'll read a bunch of things where it sounds super complicated, but it's basically a combination of doing recursion and writing things down as you go. And so you probably saw where did that slide go? You probably remember when you first learned recursion, there's the Fibonacci numbers, where if you try and compute this with recursion, it gets very slow very quickly. And the reason for that was that there's a lot of overlapping subproblems, where if you're calculating fib of 5, you end up having to calculate fib of 3 twice in this recursive tree. And so that's the problem. That's why it gets very slow, because once you ask for bigger and bigger numbers of n, then it just like slows way down. So we got there from recursion. In terms of what we need, so a dynamic programming problem is characterized by needing an optimal substructure, which means that the way to find the optimal solution is to look at the subproblems. So the bigger solution isn't easy enough. We need to break it down. And then overlapping subproblems, which means that there's work that's duplicated among the subproblems. So first, if you can find, here's what the subproblem is, then you see is this work, like, do we have to do this work twice or more than once? And if that's the case, then dynamic programming is the best approach. So it's not quite the same as divide and conquer. So if you think kind of like merge sort, where if we've got an array and we need to like split it in half, this is an example of having subproblems where we're like, let's sort the left half of the array. Let's sort the right half of the array. We split it, so there are subproblems, and the way to find the optimal solution is to look at the subproblems. However, they're not overlapping. So sorting the left half of the array has no bearing to sorting the right half of the array, right? So there are subproblems, but not overlapping. So there's a difference between pure divide and conquer and dynamic programming. So yeah, so Fibonacci, this is a dynamic programming problem because finding the nth Fibonacci number, in case you forget, the basic equation is fib of n is equal to fib of n minus 1, and it's the sum of that and fib of n minus 2. So Fibonacci sequence is 1, 1, 2, 3, 5, 8, and so on. And so when we write out the recursive tree, if we just write this naive recursive solution, we see that fib of 5 calls fib of 4 and 3, fib of 4 calls fib of 3 and 2, and so on. So we can draw this tree out for whatever value of n we're given, and we'll see that there's overlapping subproblems. So not only is you have to work backwards to kind of figure out the solution to what's the nth Fibonacci number, but we also noticed that these subproblems overlap. So dynamic programming is a combination of recursion and writing things down. Let's review recursion. So recursion, we need a base case. Remember this, the simplest possible way we can solve this problem. Any recursive call that we make needs to progress towards a base case. And ideally, this is with smaller values, so you know that it's going to end. So there's a recursive problem called, there's a conjecture called the Collatz conjecture, which to find the sequence is you start with some number and then you repeat until you get to, I think, 1. So if n equals 1, we're done. Otherwise, we call recursively on n over 2. Otherwise, we do 3n plus 1. So we multiply n by 3 and add 1. And the Collatz conjecture is that for any number, it will eventually converge to, I believe it's this pattern of 4, 2, and then 1. So that's the Collatz conjecture, that it will converge. It's not proven. If you manage to prove it, then you get instant PhD. So, but this is a recursive problem. And the problem here is with the making progress part. So if we always divide it by 2, then I would argue, yeah, we're gonna get there eventually. But the problem is the 3n plus 1, because in some recursive calls we are increasing. And so the question is, are we ever gonna get there? So typically we make progress with smaller recursive calls. So if you're working on something that you're increasing the size, be wary. And then the other rule of recursion is compound interest, where this is why we need dynamic programming, which is where we don't want to duplicate the work by solving the same instance of a problem in separate recursive calls. So this is where writing things down comes in. So there's 2 approaches. One of them is, which I believe the reading covered, is memoization, not memorization, memoization, where it's like we're writing a memo to ourselves of, as we're going along, we store the solution of what we have done so far. That way, as we go along, we come to a point where, oh, we've done this before. Then we don't have to go through the recursive calls again. So that's memoization. So that's what we call the top-down approach. So as we go along, so this is like, if we start with fib of 5, and let's say we go down the left subtree first, we'll compute fib of 4, we'll end up computing fib of 3 and 2, and then we write those down. And so we say fib of 2 is 1 plus 1 is 2. And so then fib of 3 is 0, 1, 2, 3 is 3. And so we'll write these down as we go. And so that way, when we come here, we're like, oh, I already know fib of 2. I don't need to do that again. And then when we come over here, we're like, I already know fib of 3. I don't need to do that again. So we go from the top of this recursive tree down. And as we compute something, we write it down so that we don't have to resolve it later. There's another way, bottom up, which is tabulation. And so this involves solving smaller problems first and then working our way up to bigger problems. So memoization is we start with the big problem and break it down. Tabulation is we start with small problems and then work up. And so this would involve something like, if we want the nth Fibonacci number, we have some array that we work from 0 all the way up to n. So we could say, oh, the 0th Fibonacci is 1, and then we refer to these previous ones to solve the next. So that's tabulation. So note that so if we wanted to, so maybe Fibonacci is a bad example, because I think, yeah, so as we solve the nth Fibonacci number, we need to know all the n-1 Fibonacci numbers. But there may be dynamic programming solutions where, I don't know, maybe we skip some numbers, where a tabulation approach would fill all those options in, but the memoization approach only records what we need. So that's something to keep in mind. So with memoization, the general idea is to solve a given problem, first we check if we've stored a solution to that problem. And if we have, then we don't need to do any more work. Just hand it over. Otherwise, we're going to do the recursive call. And then when we solve that problem, we need to write it down and then return the solution. For tabulation, we write the problem as a sequence of smaller problems that build up to our original one. So every problem as we go, so this is like the Fibonacci, where every problem as we go, let's say we're here in the array as we're tabulating. The way that we get this is to solve the previous problems. And so if we start at the beginning and build our table up, then we can finally get to a point where we have our final solution. So this information is typically stored in a matrix or an array of some sort. And the recursive call tends to look like we've got some of the base case, and then we leave it all the bigger problems to the recursive call. So it's just a different way to set up recursion. Okay, so let's say we are adventurers and we want to pick up items that we're going to go to another market and resell. And our packs this is the knapsack problem. So our packs can only hold so much weight. And so how do we choose the most valuable items to take that fill the pack as fully as possible? So we want to fill everything up and then go to the market and sell it all for the most money. So I've got a problem here. This is not, I don't think this is a packet problem. This is our example. So since we didn't do our speed round for this one earlier, take a second with these numbers and our capacity of 17. What do you think is the optimal choice of items? All right. Who has an answer? Yeah. Okay.
Person said you were resourceful enough with your armor. You should put it in a pan, a pot, if need be, and like cook with that, say shield, and just like put the shield on fire. Cook with that. So you can take the armor, impact, and fire fuel, and that all to go with you. But per se, say if you're going in with like leather armor, or you just don't know how to be resourceful, then maybe going down with a frying pan and armor, and then cooking the monsters you find down there might help.
All right. Okay, so 8 plus 9, that gives us a weight of 17, and the value of 11 and 13 is 24. For the armor, food, and fuel, the weight is 7 plus 8 is 15. And the value is 4 plus 5 is 9 plus 11 is 20. So this would give us, and I would say that this is probably maybe the better solution because it maxes out our weight capacity and we've got a value of 24. Does anybody have something better than 24? Okay, so maybe we found it. So one possibility to solve this is list all the possible combinations to say, here's our list of items we could take. let's find out whatever combinations are possible and then just choose the best out of that. The problem is, for a small number, that may be doable, but as the options get larger and larger, it's very, very, very much not doable. Remember, to find all the subsets of a set, that's exponential, which is not good. So keep that in mind. Maybe we come at this in a naive recursive way. This is an example that somebody has where we've got some data structure to hold here are the items. So like what number are they? What type is it? How many of these do we have? Stuff like that. And we have a recursive, so we've got the base case to say if the max weight is less than 0, then just return 0. Otherwise, we go through each of the items and we say, let's take away this current item. And then we say, okay, what's the value of my knapsack if I choose this item and whatever's left? And then when I get that back, if that value is bigger than what I currently have, then update that. And so we just do that for each item. And then we return the max value. That's a naive recursive implementation. It's not very good. So this is why we need dynamic programming. So this is a bottom-up solution for the knapsack problem, where we have some input for here's the max weight, and we have some list of items. And so for the tabulation approach, we create our solution array, and then we start with a base case. So presumably, if we have no capacity in our knapsack, then the value of that 0 capacity knapsack is 0 because there's nothing in it. And so then we look at increasing values of our maximum weight, and we do this process where we still have this kind of the basic recursive structure where we start, okay, let's assume that our max value is 0, and then we're going to see if we can do better. So for every item, check how much weight we would have left if we chose this item. If that puts us over, then we can't choose this item. So move on. And then we look at the value. So we get the value for that specific item and then find the value for everything else. And then if that value is greater than the max, then we update that. And then once we get to the end, then our solutions, we've got this new result. So given these items, we can have the maximum value for this weight. And so that's the recursive process, where we have this tabulation where for each possible value of the maximum weight, we find what's the best option. So we start at 1, then we go up to 2, and so on. Let me copy this over. Make it a little bit smaller. Okay, I think that'll do for now. Take a second and look through this code and with our input. See if you can figure out how it works. And discuss with your neighbors. Okay, so we start with the low capacity of like knapsack weight of 0 and then knapsack weight of 1. And obviously for our example, until we get to weight of 3, there's really nothing we can do. But at each step, so like at 3, then we have a value of 4. But at each step, we consider all the possibilities. So not just so here we would take a food pack for weight 3. But when we get to weight 4, we consider not only including a food pack, but also the fire fuel. So at each step, we're not limited to what we considered previously. Other questions? Okay. So I'm going to give you an overview of how we solve this top down, which is first we create, again, the solution array. And we ask, is there a solution known at this weight? If we do have it, then just return that. Otherwise, we've got a base case for if we're at 0, then just return 0. Otherwise, if we don't have the solution at this weight, set the result to be 0. And then we follow the similar process where for each item, we find, if we chose this one, find what else fits in the knapsack. And so if we chose this and it overfills, then move on. Otherwise, we do this recursive call. So first we check if we chose this item, does it put us overweight? If it does, then don't bother. Otherwise, make the recursive call. And if the new value is bigger, then we found a new combination of items and then memoize. So we're kind of doing the same thing, but it's just in slightly different orders. And so remember that with recursion, the order in which we do things can matter. It can greatly affect what solution is obtained. So if it sounds like we're kind of saying the same thing over and over again, that's because we are. It just do it in slightly different ways. Okay. Do you want to stare at this for a second and see if you have any questions? Any thoughts? Yeah.
All right, I guess it's just on top. It's like we're doing this.
Yeah, so here we start with the weight of 17 or something. Whereas before we start with the weight, I gotta go all the way back. Before we start with the weight of 0. So bottom up is we start at the beginning and work our way up to 17. And here we start at 17 and work our way down. Other questions? Okay. So in terms of which is best, it kind of depends on what system you're working with. So the person who wrote the pseudocode for this, they tested the naive recursive, which is very slow and not recommended, which is kind of what we see for Fibonacci as well. For bottom up, that's very fast. It works for many, many solutions. For top down, since we've got an explicit recursive call, then the system that you run this on might be limited for how many recursive calls we can make. And so it works up to a point, but maybe not so much after that. So things to consider as you think about how big your output could be. All right, so now I'm going to have you work with your neighbors, look up a knapsack solution online. So Google solution to knapsack problem, and try and identify what kind of problem, what kind of category, either just naive or iterative, or which kind of dynamic programming category does it fall into. Let's at least talk about the other things that we have to talk about. So the thing about dynamic programming is that it's hard, right? So chances are you're not going to understand that first go around. I know it's hard for me to understand the first go around. So I'm going to keep finding different explanations, and I'll try and bring one each class of maybe this is another way to look at it. So you should also do the same thing of, if you're struggling with a problem, go and look up how do we do this dynamic programming? How does it work? Because that's the thing about this. Like, it's not as readily accessible. It takes multiple go arounds to learn this stuff. So keep that in mind. Remember, Google is your friend. There's lots and lots of slide decks and YouTube videos and articles and explanations. So make sure that you cast a wide net and try and see different approaches. And as you do that, you'll find that, oh, they mentioned this, but maybe they left out X, Y, and Z. Or someone mentions X, Y, and Z over here, but they leave out A, B, and C. Okay, so some other things that you need to know, which is, I believe, at least one of the packet problems and will be one of the video problems, is this notion of edit distance. This is used in applications like bioinformatics and such, where if we've got this string of DNA, then we need to know how many changes do we need to make to change one of these into the other. That's edit distance. And so the example is, let's say we have two words, chicken and ticket, and we have operations. Operations include changing a letter. So let's say we had, trying to think of two words that are similar. Let's say, okay, let's make one of them cat and the other one bat. This is an example where you would change. So if you wanted to change cat into bat, you change the C for a B. So that's a letter change. You could also add letters. So if you had Someone have an example word? Otherwise, I will try and think of one. So like, I think sate is a word, like you can do sated. And there's the word sat, where if we add an E to sat, we change sat into sate. So that's additions. We can, but we can also have, like, if we have, like, let's say we have saint, and we can also delete letters. So like if we deleted I and N, then saint turns into sat. Right? And so this, if the number of operations that we perform turns one word into another. So the edit distance for cat and bat is 1. The edit distance between sate and sat is 1. The edit distance between sat and saint is 2. Because they had to make 2 deletions. So that's the problem. And so so I have some examples here. So turn to your neighbors and prove that these, or verify that these numbers are correct. So to turn chicken into, or I think ticket into chicken, or maybe both ways. It's 3. Lazy and crazy, the distance is 2. Intimidation and immigration, the distance is 5. So turn to your neighbors and verify those numbers. All right, can someone tell me which operations we need to do to change chicken into ticket? Go for it. So no C, no H, add a T. Okay. That's 1, 2, 3, 4, 5. Someone have better? Entity, yeah. Yeah. Okay, so same general process. It's just keep in mind that like changes is an operation that we have available. Anybody else get something drastically different? Okay. What about lazy and crazy? Yeah. Mm-hmm. Yeah. So then add the R in there. Yeah. And that's 2. Someone else for intimidation and immigration. Sure.
Change like the first I to an M. And then drop the N. Change the E to a G.
Drop the NT. Change the D to a G.
And then just add an R after
R.
that. I'm sorry, the second I.
Oh, yeah, okay. That makes more sense. Okay, so this I goes to an M. Then we get intimidation. And then we change the D to a G. Then we get int, or maybe we take out the N and T. and then we add 1. So that gives us 1, 2, 3, 4, 5. Cool. Sounds good so far? All right. So one of the packet problems focuses on that, also one of the video problems. So what I'd like you to focus on as we start the packet is first try and write your solutions in plain English. So this is kind of the approach for the graphs of being able to say, here's my solution generally. And having that at a level that is specific enough to mean something and also not too specific as well, like not going maybe too much into pseudocode. Then I would like you to write pseudocode. So this involves maybe you write something that looks like a Python function, which may have parameters, or you write clearly like, here's my input equals blah, blah, blah. Make it clear if you're storing information, make it clear, here's what that looks like, what form it takes, and make sure you also demonstrate where the recursive call happens if you are using a recursive call. The idea for these is I'd like to spend the class time on starting it, figuring out maybe this first part, this general approach, and as much pseudocode as you can. And then the idea is you go home and work on it. And then there's the packet document on Canvas. And so if you go and fill out this document and then submit that to Canvas. And so I'll take electronic submissions for this one. So we start on it in class. You've got the paper copy to jot any notes down and get started. And then you go home and refine it. And ultimately, you'll submit the typed copy whenever we're done with the unit. That sound good? Okay. And so again, we kind of mentioned this earlier, but for the video assignment, your group will be assigned a dynamic programming problem as opposed to explain how dynamic programming works. So I'll give you a problem and then you solve the problem. Solve the problem. And then as you do that conceptually, this is kind of where maybe the roles start to break down, where I don't just want, this is what I don't want to happen, is where the group is like, you're the architect, you solve the problem for us. That's not fun for the architect. It's not good for the group. So the architect takes lead, maybe organize and coordinates all the group getting together. But everyone should contribute in being able to solve this and understand it conceptually. And then coding as well. Once you've got this conceptual solution, hopefully coding follows. But the programmer should take the lead on that. And then again, being able to present it and understand it. Like at the end of this, every person in the group should understand, here's the problem, here's how we solve it. And so the 3 roles kind of just contribute to that final video. So this is where I want to very explicitly say that your group has to do all of this together. So as you begin this assignment, if your group is not communicating, let me know early so I can step in and be like, hey, meet with your group, solve this. Because I'm also aware that it's getting to be the end of the semester and you all have 5 million other things going on. So start this early once I assign you a problem and meet, go to a whiteboard, work it out. Does that sound okay? Any questions? Okay. That's what I've got for now. So it's packet time. So we'll start with the problem of the actor. So you're a very popular actor who's offered some number of jobs. I can pull up the. Let's see, I can pull up the example that I saw. So here, let me screenshot this part. That's very. Make that smaller. So this is an example where we have maybe assume the value is in like the thousands of dollars or something. Where we have some, maybe we number the days, and so you start at this date and you finish at this date. And something like that. So this is a sample input that you could consider. So let's say we've got maybe 20 minutes till the end of class. So let's work on this and try and find a starting point. And if we run into significant problems, we can revisit this again next class. Also, remember, Google is your friend, so feel free to search for this problem, see how others did it. All right, so we're out of time. Be looking out for an announcement tomorrow, and we'll go over this again on Thursday and so on and so forth. Thanks for engaging. I'll see you next time.